Mechanisms of climate tectonic coupling. How mountain building, climate, erosion, and rock uplift talk to one another through feedback loops. First, tectonics builds topography. Converging plates shove crust together and raise a mountain range. The new high topography then alters local climate. Air climbs the windward slope, cools, and drops rain or snow. That is orographic precipitation, leaving a drier rain shadow on the leeward side. Erosion powered by rivers, landslides, and glaciers removes mass from the range. In a critical wedge orogenic belt, the wedge tends toward a special surface taper that is just on the verge of failure. If erosion thins the wedge, internal stresses readjust, and faults can slip to regain the critical taper. Next, isostasy ties climate-driven erosion to rock uplift. Think of the crust floating on the mantle like an iceberg in water. When erosion shaves off the top, the crust rises to compensate. A rule of thumb: removing 1 kilometer of rock can induce roughly 0.8 kilometers of isostatic uplift, depending on densities. In very wet or glacial climates, unloading by erosion can add about 0.5 to 1.5 millimeters per year of rock uplift on top of tectonic uplift, as observed in places like the Southern Alps. Let us connect the main feedbacks. Tectonic uplift raises topography and steepens slopes. Higher mountains intercept more precipitation on the windward side. More water and steeper channels increase river incision and glacial erosion. Erosion removes mass and transfers it to adjacent basins. Unloading changes the stress field in the crust and can modify fault slip and wedge geometry. If erosion keeps up with uplift, a dynamic steady state can emerge. If not, the range grows or shrinks until feedbacks catch up. Climate can tilt an orogen. On a wet windward slope, erosion is focused. The dry leeward slope erodes more slowly. This asymmetric erosion can localize uplift and deformation beneath the wet side and widen or narrow the belt depending on efficiency. Examples include the Southern Alps of New Zealand and the Olympic Mountains in Washington, where precipitation patterns match structural asymmetry and rapid exhumation on the wet side. Surface unloading can also influence deeper crust. In the Himalaya, rapid river incision on the range front during intense monsoon may help extrude a weak, warm mid-crustal channel toward the surface. This can produce tectonic aneurysms, localized zones of very high rock uplift, and young metamorphism, like Nanga Parbat and Namche Barwa, where rock uplift exceeds 5 to 10 millimeters per year. Finally, it is hard to isolate climate's causal role because tectonics and climate act together. Similar geologic signals can emerge from different drivers. Even so, the European Alps and the St. Elias Range show synchronous shifts in width, exhumation, and sediment flux that line up with climate change. Remember, it goes both ways. Tectonic shapes climate. For example, the uplift of the Tibetan Plateau intensifying the Asian monsoon, and climate shapes tectonics through erosional unloading and sediment redistribution. The big picture: mountains are co-produced by tectonic forcing and climate-controlled erosion. Isostasy links surface removal to rock uplift, and feedbacks can push orogens towards steady states or into localized extremes. Integrating both climate and tectonics is essential to explain orogenic evolution.